Bottling a star is the ultimate objective of fusion research, but superheated plasma violently resists every attempt to contain it. The primary obstacle stalling fusion for decades has a specific name: anomalous plasma diffusion. Internal turbulence causes heat and particles to escape the magnetic field 10 to 100 times faster than classical models predict. The dominant strategy has been to construct expansive, heavily energized structures to overpower that chaos through sheer density and power. Yet no existing tokamak has achieved an operational regime where turbulence doesn't dictate the flow of the plasma. Building a larger cage will not tame the plasma. The strategy of relying on volume to contain chaos is hitting a physical wall. The ODTOE framework proposes a different path. Instead of fighting the turbulence with heat, it redefines the mathematics governing the movement of ions. The paper maps anomalous diffusion directly to fractional Brownian motion, treating the turbulence as a series of chaotic, random walks. This establishes a specific battleground inside the reactor, defined strictly by a mathematical parameter called R. Parameter R represents the direct ratio between directed magnetic order, or drift, and chaotic stochastic noise. The operational objective is to tilt this balance, pushing the value of R past 1. Success becomes a mathematical challenge of organizing chaos, rather than an engineering problem of size. To push the parameter R past 1, the plasma must reach a critical threshold of coherence, designated as SC. Solving for these thresholds reveals a counterintuitive reality. Physical compactness provides a structural advantage. For the 6.2-meter ITER facility, the critical coherence threshold sets at 0.87. For a compact 0.3-meter reactor, the math proves that threshold drops to just 0.10. Reaching this threshold requires adaptive pulsation, a system that alters its magnetic frequency in real time by measuring the plasma's diffusion exponent. The reactor adjusts its magnetic rhythm to match the current state of the chaos, shifting its pulse sequence as the ions begin to align. Compactness allows the reactor to operate as an adaptive conductor, syncing with the natural rhythm of the ions to reach coherence with less energy. Under this adaptive rhythm, the fractal, chaotic paths of individual ions begin to steadily straighten out. Once ballistic, these ions can thread the needle, slipping through narrow resonance windows within the Coulomb barrier that were previously unreachable. Crossing the ESC threshold triggers a shift in the plasma's state, initiating a cycle that transforms the physics of containment. Higher coherence reduces turbulence, which increases magnetic drift, and that drift, in turn, reinforces the coherence. This cycle becomes self-sustaining, allowing the reaction to maintain itself. This self-organization is so powerful that the design requires a dedicated limiter to throttle the runaway coherence and keep the plasma stable. This stands in direct contrast to traditional fusion, which requires a constant, energy-draining struggle just to keep the reaction from collapsing. We are abandoning the brute force Lawson criterion. The future isn't forcing a star into a box, but tuning it into existence through precise resonance.